All right, so I get going?
Yep.
All right, excellent. Well, thank you, Francesco, for the invitation. Sorry I couldn't be there in person. I have a 5-month-old named Nadia and a 2.5-year-old toddler. So as you can imagine, they keep us really, really busy. So when Francesco approached me in the summer, it was like, I don't think I can be there in person, but I'm glad that we can do this virtually. I'm also currently running a field experiment. I'll talk a little bit about that. We still don't have any results because we still don't have the data with us, but definitely would not be able to be there this time of the year, but hopefully sometime in the future. All right, I'm gonna get going with my talk about directional kinematics of breaking surface gravity waves. So in terms of motivation, I think we all know that the ocean plays an important role in regulating our weather and climate. And right in between the two systems, atmosphere and ocean, we have ocean waves. And we know by now that ocean waves play a pretty important role in modulating air-sea exchanges, exchange of momentum, energy, mass, gases, and heat. So if we want to improve our ability to predict weather and climate, we have to do better at being able to predict surface wave processes. And ocean waves are also important for other areas like remote sensing, underwater acoustics, as well as for ocean and coastal engineering. So I'm going to set the stage talking about the evolution of surface gravity waves with the radiative transport equation. So this one describes that energy will, if we neglect the presence of currents, energy will propagate at the group velocity, and my pointer is extremely slow. So I may not be able to point correctly, so I'll try to just keep it in place. We have the advection at the group velocity of the energy spectrum. On the right-hand side, we have our source terms. We have the wind input, wind forcing by the wind. SNL is the non-linear resonant wave-wave interactions. And the third term is the dissipation due to breaking. In deep water, these are the essential three terms that govern the evolution of waves. And so I'm not talking about shallow water waves breaking at the shore. We'll be talking about deep water breaking waves. So here are the main source terms at play. And just to also introduce some of the terminology. So if you have a two-dimensional wave field, you can decompose it into its Fourier components and compute a directional wave number spectrum. In this case, if you are if your data are in space, you could also do that in frequency. And the area under the curve gives you the variance of your series surface elevation if you integrate your spectrum overall wave numbers, and you multiply by rho g, and you get your energy per unit area. Now, if we integrate a spectrum as smoothly, you will find that it has two main regimes. One, equilibrium range with a power law of k to the minus 5/2, followed by a saturation range with a power law of k to the minus 3. And each of those regimes have different controlling dynamics. Within the equilibrium range, all three terms are dominant. So wind input, wave-wave interactions, and dissipation are shaping that spectrum. And actually, the wave-wave interaction is the term that is by far more important for setting the shape or controlling the overall shape of the spectrum. And all three terms are important, are the dominant terms in this equilibrium regime. Then in the higher wave number, in the K to the -3 or the saturation regime, the overall magnitude of the wave-wave interactions when integrated in azimuth is not as large compared to the wind input and the saturation and the dissipation. So you have a primary balance in the higher wave number between wind input and dissipation. So these are just things for you to keep in mind as we go forward. But again, the wave-wave resonant interactions are really the key term that controls the shape of the spectrum. And we've known that for a very long time, but there are some limits as to how much can that term reproduce the observations. And that's where some of this work comes in. Continue talking about the shape of the spectrum. We've also known for quite some time that, so imagine you have your wave number spectrum here in 2 dimensions, kx, ky. This is wave number, tells you how much variance there is at a given wave number and direction. If you then translate that into a k theta space, so this could be either in Cartesian or polar, but going into a k in the vertical and theta in the horizontal, you will immediately realize that there is some azimuthal bimodality in the shape of the spectrum. So we've known that for quite some time, that the spectrum is directionally bimodal when you go from the spectral peak into the shorter scales. And the same happens when you go into longer scales than the dominant scale. And that the main mechanism responsible for this bimodality are the wave-wave resonant interactions. And I will show that in a minute as to how that works. So something I forgot to mention is that the wave-wave interactions are responsible for the energy cascade. So there's forward energy cascade, taking energy from intermediate scales, taking it into the smaller scales. But there's also the inverse energy cascade, which is making our waves to get longer and longer over time. So you can see that the SNL, it's negative in the center, but then it's positive at lower wave numbers and also at higher. So it's kind of like in the world of turbulence, 3D turbulence, you get forward energy cascade. 2D turbulence, you have the inverse cascade. Here in the world of gravity waves, we have both cascades happening at the same time. And the nonlinear transfers are responsible for that transfer. Now, this azimuthal bimodality that is primarily controlled by these wave-wave interactions, a very nice way of visualizing it is if you then normalize your spectrum by the maxima at a given frequency or wave number, you begin to pick up these structures. This is what Ian Young in 1985 did to really emphasize this bimodal structure when you plot it in a theta. In this case, it's frequency and not wave number. And so you can see very clearly this bimodality happening. So you have maxima around the spectral peak is very narrow and unimodal. But once you go into the higher wave numbers, you have a very clear bimodal distribution of the energy. Subsequently, more measurements became available, especially measurements in the spatial or spatial temporal domain, that showed that this bimodality, once you get into the short gravity range in the, say, order scales of a meter or so, you begin to get really, really extreme lobe separations. And these lobes can reach such big angles of plus or minus 80 degrees. So you actually have energy going in opposite directions because each of the lobes is such wide amplitude in terms of degrees, plus or minus 80 degrees. So you have substantial component of that energy going in opposite directions. And I said earlier that two leading order is the wave-wave interactions that control this bimodality. Now, for many years, we were unable to reproduce such extreme bimodalities. Any efforts solving for this radiative transport equation using our exact methods for the wave-wave interactions could not reproduce these extreme bimodalities that we observe. And the only way that we have been able to do it up to now is if the dissipation function happens to be narrower, significantly narrower than the energy spectrum. If that's the case, if your dissipation is azimuthally narrower than the spectrum, it then couples with the wave-wave interactions and allows for this increased bimodality to develop. And I'm going to show you examples of solutions. So this is with this narrow dissipation function. So on the left, I'm showing you the directional distribution that comes out of the solutions, giving rise to this extreme bimodality. On the right, I'm just showing you the directional distribution, or basically the directional nonlinear energy transfer. So remember, we had a forward and inverse energy cascade, and you can still see it very clearly in this 2D diagram. You still are taking energy at intermediate scales. You're putting them into longer scales or lower frequencies, but you're also taking it into higher frequencies. There's also some directionality happening. Some of the energy that you're taking from intermediate scales, you're putting it at an angle at higher wave numbers. And that's part of what's driving this bimodality. Notice that the amplitudes are relatively weak. And so what happens when you force the model with a broad dissipation, the wave-wave interactions are never happy. They're always trying to push energy sideways azimuthally. And as a consequence, so here I'm showing you solutions using the standard models in the literature. So Ardois et al. 2010 is used operationally around the world. So does Liu et al., which is the ST6 package in WaveWedge 3. And so both models, when you run both of those models, they assume that the dissipation has a directional width that is identical to that of the spectrum. So it's going to be very broad. And what happens is that the wave-wave interactions are really trying really hard to make the spectrum broader and to create the enhanced bimodality. If you force it with the narrow dissipation, it gets to the point where the wave-wave interactions are actually happy, and the magnitude of the lateral transfers are relatively small. It's a self-stabilizing effect of the wave-wave interactions. If you perturb it in a way that it doesn't like it, it's gonna start moving energy around until it's happy again and its amplitude is gonna be reduced. So it's a self-stabilizing effect, and it's pretty obvious in these comparisons. Now, what it's interesting, if you integrate these nonlinear transfers in azimuth, all three have about the same amplitude. So this is the nonlinear transfers integrated in azimuth. And notice that the order of magnitude is about the same in all three. Yet in the 2D world, you have really large fluxes going laterally, but when you integrate in azimuth, some of that cancel, the pluses cancel the negatives, and so you don't see that if you plot it only in one dimension. So this is really emphasizes the self-stabilizing effect. Once it's happy, once the nonlinear energy transfer is happy, the magnitude of the exchanges laterally are reduced. And that has been observed in other experiments like Recio et al., where they would actually perturb the spectrum away from for example, the f to the -4 or k to the -5 halves. and it will bring the spectral shape back to its preferred shape, and the overall magnitude of the wave-wave interactions reduces. And so this really emphasizes the need that we need to better understand the directionality of braking if we want to be able to improve the models that we use routinely in operations. Now, you could also argue, well, a narrow dissipation is giving better results, but couldn't you do the same, achieve the same result if the wind input was broad instead of reducing the spreading of the dissipation? That could be possible. However, what I think the challenge is with being able to confirm some of that is, for example, how are we going to measuring the braking waves is a lot easier than measuring the wind input, which is the work done by the wind. So I think at this point it's worth spending some time and looking at the directionality of braking to see if we can better constrain this directional energy balance. And so this is what motivated some of the work that I'm going to be presenting today. And I'm very grateful that the community welcomed it, and we currently are funded by NSF to do some observations, collect some data to tackle this problem. Today, I'm going to show some of the results that we have preliminary using open source observations that are available to us, but we are in the process of collecting more data so we can really tackle this problem better. So our framework for quantifying the statistics of braking is Phillips's 1985 lambda of C distribution. And what this is the length of braking fronts moving with velocity C to DC, such that if you integrate it overall velocities, you get the length of braking fronts per unit area. Now, one of the beauties of that distribution is that each of their moments can be related to different physical processes that are happening at the ocean interface. First moment can be related to the braking probability. The second moment, you can relate it to the whitecap coverage, which is the area covered by actively braking waves. Third moment is related to the air entrainment. Fourth moment related to the momentum flux. And finally, the fifth moment is related to the energy dissipation. So if we can measure these propagating fronts, the whole premise is that then you can relate the propagating speed to the scale of the waves. Now, we know, and I was going to have a slide about that, and I forgot to do that. We know that the waves actually slow down when they break. But we know that is roughly within 20% or less that the velocity of the braking front related compared to the actual phase speed of the wave. So we are within the 10 to 20% error in C, and then you could argue that, well, at 20%, if you raise it to the fifth power, it contributes to a very large error. Yes, but I can't think of any other better framework to being able to do this work. So that's the disclaimer right there. And I'd be happy to discuss that in more detail. So just to set up the stage, I have this recording from the measurements we are currently collecting. Let's see if this is going to work. It's a classic video that never works. And there we go. So this is data that we collected. We just collected it a few weeks ago. We have the cameras out in Martha's Vineyard. I will talk a little bit about that, but I wanted to show this video. This is one of the biggest breakers we've seen in our data. This is in 10 meters per second winds, 2 meters significant wave height, and the peak wave period is 8 seconds. And I think it's very helpful really just to set up the stage, to just give you a sense of how complicated the waves can be and the breaking process, and that the methods that we're using are trying to simplify a very complicated problem. So in order to compute this lambda of C distribution, we have to be able to basically track the individual breaking fronts, calculate their length, and then do ensemble statistics. Something that might have been clear, I'm trying to play it again and I'm unable. Let me see if it's gonna work again. So that was a dominant breaking wave. So this was the biggest scales at play. But what you might have been able to see is that there were also smaller waves that were breaking on the crests of the bigger waves. And that's probably one of the most important problems that needs to be tackled next. And most of the analysis that I'm going to be presenting, that's work being done by Bernard Akawase, who's a PhD student in my labs. So any questions that you may have that are too technical, please reach out to him. His email is here, and I'll put it at the end, again, in case you have any questions and you want to reach out to him. So the two data sets we have been analyzing for the last year or so are open access data collected by other groups, specifically data collected by Alvise Benetasso at Acqua Alta Tower in Venice, Italy. I know Francesco has worked with data collected at that tower as well. I don't think it's from that paper. I think the data that Francesco might have worked is in 2013. This is from 2015. Conditions are 13 meter per second wind, 6-second waves with 2-meter height. And for this data set, both the wind and the dominant waves are aligned. Keep that in mind. The second data set we analyzed is from the Black Sea. That data was described by Leckler et al. In 2015. In this data set, the waves are smaller and shorter. And more importantly, the dominant waves and the wind are not exactly aligned. There's a small misalignment between them, which is relevant for the sort of question we're trying to answer as to what is the preferred directionality of the breaking waves. So that's going to help us address some of those questions. Now, for computing the sea surface elevation from this stereo imagery, we're using the WAS system, the Waves Acquisition Stereo System, developed by Alvise Benetasso and Bergamasco et al. This is open source and has been developed specifically to be used over water to track actually ocean waves, and has been used extensively by different investigators, including Francesco.
Actually, that is my project. I started using VAS for oceanographic application. It was my first project at Georgia Tech. I'll send you more information. Maybe you are not aware of that.
Okay, cool.
So it was my idea to use VAS at Acqua Alta to measure ocean waves. It was my first project funded by Chevron here at Georgia Tech in 2008.
And was that on extreme waves?
Yes, that's where everything started, and then they move, on and did that applications, But I'll send you the reference, So maybe you are not aware, you didn't know about that.
Okay, yeah, it's been very, very useful.
I know, and
for everybody, for the whole community. I think there was some skepticism at some point, but I think it's proven otherwise.
Yeah. I'll send you the references.
Cool, thank you. And so one of the advantages of this WAS system is that it does most of the work for you to get a three-dimensional point cloud. It does the feature matching, It can also do the extrinsic camera calibration, which basically tells you the position and orientation of the camera, so you don't have to worry in the field when you deploy your cameras. You want to get them aligned as close as possible, but you don't have to sweat whether I know exactly to the most precision possible the relative orientations and positions. The software will do it for you, which is it's very helpful. Does the triangulation, and then you get the 3D point cloud. It works very, very well. So from those 3D point clouds, we get directly the sea surface elevation. And for our problem is great because we get the surface elevation in addition to having the visible imagery superimposed with it. So we know whether the wave is breaking or not, so we can compute our breaking statistics. Now, something that I will touch on later, right now for this visible imagery, we are relying on waves that can produce bubbles, being able to detect them. But once you get into the meter scale or so, there are waves that are going to be breaking, but they're not entraining air. So we would miss those with this visible imagery. And to be able to detect those, you need other technology like infrared imagery. All right, so to compute our spectrum from this Aqua Alta data set, our approach was first we grid our data in our X, Y, Z plane as a function of time. And notice that the dominant waves are really big compared to our window size, so we can barely fit one dominant scale, two crests. And in order to get better directional resolution at the longer waves, then we used a two-window approach. So to get the lower wave numbers of the spectrum, we use the green window, whereas for the higher frequency, we use the purple window. And the motivation for that was that the smaller window is closer to the camera, and therefore the errors and the accuracy of the data are much better. So smaller errors and better accuracy in the near field. So we use that for the higher wave numbers. We compute two spectra, and then we blend them together with a ramp function. All the data are tapered at the edges and zero padded thrice to improve a little bit even better in the resolution. And just to give you an idea of how the arrows grow away from the cameras, so it's very, very clear here that in the near field, you have the smallest errors. When you go far away, the errors increase. And so we constrain the total energy to the variance of the smaller window. So that way it guarantees that the energy under the curve should be matched. Okay, so then our analysis is primarily done in the wave number domain. And we then compute the unambiguous directional wave number spectrum by multiplying our basically wave number frequency spectrum by 2 and integrating all the resolved frequencies. So by doing so, we get a directional spectrum that is not ambiguous. So the contrast would be, imagine you have two-dimensional images like we did with airborne work that I did in the past. If you only have a spatial information and no time information, and you compute spectra from that, you have 180-degree ambiguity. Your spectrum past 180 degrees, it starts to repeat itself. The advantage of having the time information is that the wave number spectrum that we compute is unambiguous. We get full 360-degree information, which is very, very important for this work, because again, the bimodality that I was talking about, it's approaching plus or minus 90 degrees. So using only the spatial information, you get into the ambiguity that you can't get as good of an estimate if you compare to having both space and time that is not ambiguous. So that was a very important requirement for this work. So here is the spectrum computed from aqua alta in the wave number, in the horizontal. The angle is in the vertical, and you can clearly see the bimodality that we discussed earlier, and reaching pretty large values, almost plus or minus, approaching plus or minus 90 degrees. It's not quite, it's less than that, but it's very extreme. Now, if we integrating our spectrum is in azimuth, I introduced that earlier. So here are the two spectra that we've analyzed, the one from the Black Sea in light blue. Remember, those are smaller waves and shorter waves, and the aqua alta in dark blue. Now, remember I talked about the equilibrium and the saturation range. Our resolution in K is not good enough to fully resolve the equilibrium range, but nevertheless, if I draw lines based on empirical data of the equilibrium range and the saturation range, both data sets land or overlap within an empirical estimate of the equilibrium range, so of the saturation range. So they are consistent with the literature, but you don't really clearly see the equilibrium range as I showed earlier. From those were airborne measurements with very fine resolution in K. But what we really care about is in the tail and the directional information. So we know that we don't resolve very well the peak of the spectrum, but all we care about there is what is the actual direction of the longer waves, whereas we do care about the details of the spectrum in the higher wave number that is very well resolved. Now, to compute the lambda of C distribution or the breaking kinematics, we followed published methods, the method specifically by Kleiss and Melville, followed by Sutherland and Melville, and then Bresica et al. In 2022. We first have to remove the background brightness so they make the images more homogeneous. You cannot work with any images that have glitter, because if there's glitter, you're gonna consider that as a breaker. So the quality of the images is very critical, that is good. There cannot be any glitter. We then georeference the images into an X and Y along the C plane. We track the breaking with optical flow, and we can start computing our statistics. So for each vector, we incrementally compute the length of the crest and its velocity. We add up the entire 30 minutes of data. We divide by the total area and our discretization in velocities, delta CX and delta CY. So again, both data sets that we've used are 30 minutes long, roughly 20,000 images at 12 hertz. It's a lot of computing. It takes a lot of time, but computers are getting more and more powerful, so pretty soon we'll be able to process a lot of these data sets. All right, so here are the results of the directional breaking kinematics. This is for the aqua alta. So on the left-hand side, I'm showing you, this is the lambda of C distribution. Remember now, C is the velocity. That means that high velocity means longer waves. Low velocity means shorter waves. And it increases towards shorter waves. We've known that for quite a while. If we integrate that in azimuth, the data in a narrow range, it follows a C to the -6. That's a scaling that was introduced by Phillips that would correspond to the equilibrium range, where the spectrum goes as K to the -5/2. So notice right away that the directional spreading of the breaking kinematics is relatively narrow. Remember that the spectrum was showing very broad energy distribution in azimuth and bimodal, whereas the breaking kinematics are unimodal and much narrower compared to the spectrum. So here is the same. So now here is the spectrum normalized as I introduced earlier. So you normalize it by the maxima for any given K to really bring out the bimodality. So that's shown on the left, and we flip the axis. So now the low wave numbers, meaning the longer waves, are on the right, the shorter waves are on the left. You clearly see the bimodality approaching plus or minus about 80 degrees, compares well with the Peru et al. Parametrization of the bimodality. And then on the right, we have the normalized directional distribution of the breaking statistics. So these are much, much narrower than the energy spectrum, and on average centered about the wind/wave direction. Remember, for this case, both the wind and the waves are aligned. The dominant waves and the winds are aligned, and breaking happens to be aligned in that direction. And it's azimuthally much narrower. Now, if I just show you single cuts through those two distributions in pink and red, I'm showing you the directional distribution of the breaking statistics. In blue are the directional distribution of the energy spectrum. Again, the breaking is very narrow, centered about the mean wind/wave direction, whereas the directional spectrum has this bimodal distribution and is a lot more broad. If we compute the half width of the distributions, both the energy and the breaking, we get that the spectrum increases to up to 70 degrees in half width, whereas the breaking statistics is around 30 degrees, maybe reaching 45 degrees. So it's the difference is fairly significant. Now, how does this compare to solutions generated with the narrow dissipation function? So here is a one-to-one comparison under similar conditions for idealized simulation. The blue is the computed spectrum on the right, and the red is the breaking dissipation used in that model. And they're comparable. Clearly, the breaking statistics keeps increasing towards smaller scales, whereas the model dissipation seems to flatten and be fairly consistent. But qualitatively speaking, both data sets seem fairly similar. Now, if we compare these to the standard models that are widely used operationally, those models essentially assume that the dissipation has the exact same directional spreading as the energy. And as a consequence, both the energy spectrum and the dissipation have the same spreading, and both are narrow. It's interesting that all three models give about the same amplitude in spectral and in width for the dissipation, but the big difference is that for the narrow dissipation relative to the spectrum. So that's the key difference here, that the dissipation has to be narrower than the spectrum. Otherwise, your solutions will tend to be narrow and you cannot develop the bimodality, or as broad as of a bimodality. Now, when we look at the other data set from the Black Sea, where the dominant waves and the wind are misaligned. So here on the left, I'm showing you the directional distribution of the spectrum. It's weakly bimodal once you get into the higher wave numbers. We don't see that enhanced bimodality, and the explanation for that is because we're unable to go too far away from the spectral peak. Remember, these are shorter waves. We hit the noise around 2 radians per meter, so we can't go far away where you would expect that extreme bimodality. It's just that the resolution we have short waves, and therefore we reach the noise floor too soon before that full bimodality could be there. We need more data to confirm that. But at least if I plot an existing parametrization based on my observations, are in pretty good agreement that you wouldn't expect such a broad bimodality, which is shown in red. That's based on the measurements I collected in the Gulf of Tehuantepec. Those never reach extreme bimodality because we had a limited cutoff from the LiDAR data that I used. The purple shows the peak wave number. We initially thought it was a single peak. Then we realized that that data set had been analyzed in the past by Lecker et al. And subsequently by Guimarães Vera, and they had noted that that data set actually had 2 peaks at low frequencies. So if you do the analysis in the frequency domain, you can actually better resolve those 2 peaks, and those are shown here with purple. So that would be the direction of the longer waves. Both are equally energetic. The black line is the wind direction, and then on the right is this normalized breaking statistics. And what we're finding is that the data are centered closer to the longer dominant waves compared to the wind. And so one of the implications for this is that the breaking, at least for the scales that we can resolve, is very likely controlled due to long wave, short wave modulation, and that needs to be further analyzed in more detail. We need more data with misaligned wind and waves so we can further confirm this, that in general, you would tend to have breaking center around the direction of the longer dominant waves. Okay, we're getting close to the end. So we are currently, we deployed 4 cameras, 2 infrared and 2 visible of Martha's Vineyard in the air-sea interaction tower. The deployment was done almost a month ago. We're hoping to leave the cameras out for another couple of months until we fill up the hard drives, recover the cameras, reassess, and redeploy in the spring. What do we expect? So here is a figure by Sutherland and Melville, who used infrared and visible imagery, data that they collected from FLIP. And what you can see is that once you get into the smaller scales, the visible data begins to roll off because the short waves do not entrain air. Whereas if you keep track of small scale features that can be seen in temperature gradients in the IR, your breaking statistics keeps going up because there's a lot of micro scale breaking happening at all times. So it's orders of magnitude higher once you get into the meter scale. And in that paper, Sutherland and Melville, they provided some really, really good measurements of lambda. Has been very useful for the community. They also provided a empirical scaling that really allows you to start making predictions about this lambda of C distribution, but they did not look at the directionality of lambda. And that's what we're trying to do. We're trying to look at what happens to the directional distribution at the 1 meter scale that you cannot observe very well with the visible imagery. And we're hoping to have also subsurface TKE dissipation measurements. This is in collaboration with Alejandro Cifuentes here in our department. Zed Zippel is also collaborating in this effort. And it's actually nice because it's cabled, it has power, and it has internet. So I can be sitting here in my office collecting data, monitoring conditions, and I don't have to be there. It's great. And just to give you a sense, so here's an example of an image we collected. So you can clearly see the breaking wave in terms of the foam. And if I superimpose the infrared image, you can also see a red blob right on top of it, right on top of the white cap. But there are also red crests that are not producing bubbles. So these are the signatures of micro breaking. And what happens is that you have a skin cool layer under the influence of the wind and evaporation. And every time you get micro breaking, you basically create micro upwelling and they appear hot. And that's how we're able to see these micro breakers, thanks to the skin cool layer. So I'm gonna leave it at that. Just to summarize, what we're finding is that the kinematics of breaking are azimuthally much narrow compared to the energy spectrum. And that could help improve wave models that currently tend to give much narrower directional spectrum. We also find that breaking is more, it tends to prefer the longer dominant waves, which points to long wave, short wave modulations. But we need to do a lot more work on that. We need more data over a wider range with visible and IR, different conditions, especially misaligned mean winds and dominant waves. And more importantly, we really need to do not just lambda of C statistics analysis, we have to do wave coherent analysis to really demonstrate that, yes, the breaking is happening at the crest and in which direction. So that's something we're gonna be tackling in the future. And if you have any questions, technical, please reach out to Bernard. His email is right there, and I'm very grateful for the community and NSF for supporting this work. So I'm gonna leave it at that, and I'll welcome questions.
Thank you. So, any questions from our friends online? Abigail, Cole, Ying.
Okay, thank you very much. Very nice, very nice presentation. And I work with Guillaume Ducrozet in France, in Saint-Laurent.
Share your screen so we can see you if you can.
Okay.
So who is are you a PhD student?
Yes, now I'm a PhD student, work with Guillaume, you know.
With me?
With Guillaume.
Guillaume?
Yes, in École Saint-Laurent in France.
Okay.
Okay. I just have a comment about the phase speed you compute. Now we are develop something, use the multi-directional Hilbert transform to compute the wave phase speed. Maybe you can also have a try to use multi-directional Hilbert transform to compute the wave phase speed. Maybe not sure it's helpful for you.
I'm not sure I understood the question, but so we assume that the breaking speed equals the phase speed, and then we can use the dispersion relationship to relate that to the scale and the frequency. We know that there is this 20%, up to a 20% difference. And at times, if needed, we can always do error propagation or look at what is the impact of that 20%. But
so you don't track the breakers in physical time?
Yeah, we do track the breakers in physical time. And at some point, the breaker, the phase of the long wave leaves the shorter breaker behind. Does that make sense? Yeah, so we can't, and we're planning on looking at that at like that if we look at cases where they're just starting to break, can we look at the phase speed before and after, for example? So we can do that. And
how do you compute the phase speed?
So that's the other challenge. So for the dominant scales, you can do it with, you bandpass your spectrum, you get a nice clean phase, and then you do a Hilbert transform, and your d omega dt and the omega dx You divide those two and you get your phase speed.
But it's not theoretical, it's not the exact crest speed. So the phase speed is not equal to the crest speed, and so it would anyway. I'll send you.
Yeah, so if you band pass it, then so you could do it for the dominant scales only.
Oh, okay.
And then you use the phase information of the crest itself.
Why you don't?
But it has to be narrow passed.
Okay, but why don't you get the true crest speed that you can get from tracking waves in physical time? Is very hard to estimate from the. I'm talking about you're gonna get the physical speed. You do the tracking, and you can do the xt plus 1 minus xt divided by delta t. So I mean that's what we did in 2010 with Alvise. We did with Mike Banner. So basically tracked the crest. Here in your case, you do the breaker. No.
Yeah, for the longer dominant waves, yes. For the shorter scale, then it gets into how do you decompose it into the different scales? And there are different techniques like empirical mode decomposition, like the Hilbert-Huang.
I would be careful with that stuff.
Then there's Banner used the riding wave removal. It was a slightly different way of doing the decomposition. Yes. So that's where it gets pretty tricky. So the longer waves, yes, you can see it very well. But once you get into the higher wave numbers, it's pretty difficult to decompose in a way that you trust.
There was a paper by Mike Banner and Russ on the way you sample the breakers to do the lambda C. So I remember originally, Melvin, in the original paper by Melvin, I don't know if you were involved with that paper. So they were accounting for all the breaker speed even after breaking. And that kind of bias the lambda C, because of the slowdown of the breakers. So I wonder if, when you track these breakers, do you put all the crest, all the speeds of the breakers over time into your pot to do the ensemble and do the statistics, or just at the peak time? So I don't know what.
No, we're not doing the banners to try to get the maximum speed of the time series of the event. We're just using the Price and Melville, which is just the incremental. At any given point, you combine all the events. You don't do it by individual events, but just instantaneous snapshots, and then use ensemble average them all together. And yes, the crest will slow down over the breaking process, and so then you start assigning some of that energy into different scales.
Yeah, exactly. So so you will have some bias in your estimates.
There will be some bias. It's just that the other way of doing it is also a little bit arbitrary.
But it will be nice to compare it,
Yeah, that's a good point. That's a good point.
I mean, it's like, I don't know. So it's
don't trust anyone. Do both.
Looks like this lambda C, is a sampling issue. So how you count the breakers, and there are many ways, and depending on how you count them, it's gonna give you different statistics. The point is which one is the physical counting that is gonna give us. Is going to be able to relate this gamma C to the lambda C to the physical property of dissipation and momentum. And I think this question is still, I don't know if someone answered this question.
I don't think there's going to be it's just at some point you have to make a decision and then everybody has to agree. And that's the challenge.
Yeah, but then it doesn't mean that the counting that you choose is gonna relate your lambda C to the true dissipation and momentum. So
yeah. So in my experience, what gets most affected is the level of the lambda. So it would then affect what's the breaking strength that you need to close the energy budget. In terms of the directionality, though, what we are finding is that the spreading information that we find, for example, is almost identical. It's very, very close to what Gemrek et al. Was finding using a very different method where he was doing event by event and fitting ellipses. And also assigning it to a given event, not the incremental method. Yet the directional distribution of his distributions and what we're finding and Clyde's found, they're all very, very similar. So at least in terms of the directionality, it doesn't seem to be dependent on the method.
But the question is that do you have measurements of the dissipation? So,
Okay, so at the moment we don't. Peter Sutherland did some of that. He did have coincident measurements of the TKE dissipation underwater and the breaking statistics above to being able to close the two. And at the moment, we do not have those measurements out there, but we are planning to deploy TKE subsurface measurements near the surface for the spring deployment.
thank you. Any questions from the audience in the classroom? Okay, thank you very much, Leonel. So I'll thank you for. We have. I gotta go to teach